Well, hello class. Good morning, good afternoon, whenever you read this. Hope you're doing well. This particular topic, apparently I messed up. Someone told me that I messed up on the factoring, so I want to go through this again to make sure that you understand it. Make sure that you know how to do it. I hope you don't give up all hope, because I think I just made one small mistake and I think y'all can do it. So remember yesterday it says the rate of change is given by blah blah blah. Determine the change in altitude during the time the altitude is decreasing. So remember I said write the equation, but that's wrong because I want to know the altitude is decreasing. And I can't do this formula until I know when the altitude is decreasing. So I crossed that out and I said, hey, set your derivative, remember this is a derivative function, equal to 0. And then I said, let's find the critical numbers and factor. So this is where I went wrong. What I should have wrote, and you could, if you have your notes from yesterday, you could cross that out, or if you didn't even write it down. But to factor it, what I'll write instead is, here, I'll write it over here. What I should have wrote was t minus 3 and t minus 1. Equals 0. So sorry for messing it up. So that means my new critical numbers shouldn't have been negative 4 and 1. My critical numbers should have been 1 and 3. Okay. So now I will take my number line. Remember, this problem says from 0 to 7, and I have two critical numbers. So 0, 1, 3, and 7 is what I'm going to put on my number line. And I'll test some numbers. So I'll test 0.5 here. Here, I'll type it out. I'll test 0.5 here. Between 1 and 3, I'll test 2. And between 3 and 7, I'll test 4. All right. So remember, you take these numbers and plug it into my derivative. Remember, I factored it out here. So 0.5 minus 3 is going to be a negative number. And 0.5 minus 1 is also going to be a negative number. So this whole area, this whole segment is positive. If I plug in 2, 2 minus 3 right here is negative. And if I plug in 2 in here, it's positive, which means this whole segment here is negative. And lastly, 4 minus 3 is positive, 4 minus 1 is positive. Essentially, it's positive, positive, and this whole area is positive. So now, what I should have wrote is determine the change in altitude. Determine the change in altitude during the time that altitude is decreasing. The only time it's decreasing, if I look at my number line, is between 1 and 3. Okay. So what I'll do is, let's see if I can delete some stuff here. What I'm going to do is oops, oh well, we don't do that. We just know it's between 1 and 3, so my new problem, instead of writing this formula, what I should write is between 1 and 3 of t squared minus 4t equals f of 3 minus f of 1, and that's because that's the area where it's decreasing. And then I was telling you before, it just says determine the change in altitude, so I don't have to solve for f of 3. I'm not solving for f of 1. I want to know what the change is, so I'm just going to call this whole term right here, this whole quantity, I'm just going to call it x, because I'm trying to find the change. Then you take the antiderivative. You've done this plenty of times, so I'm not going to do it for you, but take the antiderivative, plug in 3, plug in 1, and subtract. The one I wasn't able to finish yesterday is this pizza problem. Let's go back to it again. I think you all know how it starts. First of all, you'll notice that I'm going from 0 minutes to 4 minutes. So I'm going to call this 0 to 4. Here's my equation, negative 3 radical t. It's changing at negative 3 radical t. And one thing I keep forgetting to write, and it's okay because I think you guys inherently know it, but there should be a dt right here. Remember, I can't take the antiderivative. This sign has to match with this. Equals, now, you already know it's these numbers, or these numbers should match with the ones over here, so f of 4 minus f of 0. Now, let's fill in what we know. So what we know is that f of 4 is what we're looking for. It says to the nearest degree, what is the temperature at t equals 4? So if we're asking what's the temperature at t equals 4, I'm saying, what the heck is this quantity? F of 0, this is where people get confused. You know, I want to know what the temperature of the pizza is at 0. Some people look at this and say it's 400 degrees. Then some people say this has 75 degrees. Which one is it? This one says 75 degrees at t equals 0. It says the pizza is heated to 400 degrees. Which temperature was it at 0 degrees? Well, if you really study the problem, if you really think about it, we're looking for the temperature of the pizza. It says the pizza is 400 degrees. It says it's placed in a 75-degree room, which actually is a piece of information that is not necessary to the problem. What they really want to know is what's the temperature at 0, and the temperature at 0 is 400 degrees. Like so. Some of you may be confused. How do you do this? Do I need to use u substitution? The reason you don't have to use u substitution is because there's no function down here, right? Unless if this was 2t or t squared or 2t plus 1, then I have to do u substitution. But since this is just a regular t, I can take its antiderivative. I notice a coefficient out here, -3, so the very first thing I'll do is factor out that -3. I'll make it from 0 to 4. And instead of saying square root of t, I'll call it t to the half. Okay. I'll take its antiderivative. You know that the antiderivative of t to the half, I will raise it by 1. So 1/2 becomes 3 over 2, right? Raising it by 1 makes this 3 over 2. And then when I divide by 3 over 2, I get 2/3. So I will take my let me put the dt here. When I take the antiderivative, that integral sign disappears. I now have a bracket. This now becomes 2/3 t to the 3/2, 0 to 4. I'm out of space, so I'll continue here. I will factor out this 2/3. You'll notice if I factor out a 2/3, these 3's cancel. So I'm just going to get a -2 once I factor out this 2/3. -2. And then I'm going to get 4 to the 3/2 minus 0 to the 3/2. So remember, I plug in 4 and I plug in 0. And you already know 0 to any power is going to be 0. 4 to the 3 over 2. Let me calculate it real quick. 4 to the 3/2 is 8. So this left side becomes -16. So -16 equals x minus 400. I now add 400 to both sides to get x by itself. 400 minus 16 is going to be 484. Or sorry, 384 equals x. So what I found is that the pizza, if I take a 400-degree pizza, put it in a 75-degree room, after 4 minutes it'll become, or its temperature will be 384 degrees. And I know some of you will say, let's buy pizza and try it out, but it's just an example, so hopefully you guys understand. I'm going to skip over the city beside a river one, and I want to do one that I think is very challenging for some of you. It's a very conceptual problem, so the math isn't very heavy, but it's strong on understanding. So the squirrel starts at building A at time t equals 0 and travels along a straight horizontal wall connecting to building B. So if you want to draw a picture, I can't draw a squirrel, but there's my squirrel, and it starts at a building and it's going down a horizontal wire connected to building B. So imagine with your great creativity this squirrel looks like a pork chop, but this squirrel, okay? And it's traveling along a straight horizontal line connected to building B, so B and A. Alright, for 0 to 20, the squirrel's velocity in feet per second is modeled by this piecewise linear function. So this function tells me the velocity of the squirrel. Okay, so if you are visual learners, here you go. That's the velocity of the squirrel. Question A, after leaving building A, the squirrel realizes it left its acorn back at building A and returns to building A. At what time does the squirrel turn around and head back to building A? Give a reason for your answer. So looking at his speed, I'm trying to figure out when did he turn around and head back to building A. So I'll give you two options. Some people will say it's this one, and some people say it's this one, and some people say it might be this one. So when does a squirrel turn around and come back to building A? So let's think conceptually. If you're a squirrel or you're a regular person and you're running, okay, and you run, and you want to go and you forget something, so you have to stop and go back and get it, right? So if you think about the process of that, when you run, you're speeding up. So my velocity is speeding up. But then when you realize that you forgot something, you slow down a little bit. It's like you're like, oh man, I forgot something. So you slow down, and then you stop, right? And then you run in the opposite direction, which means your velocity is negative. So follow along with me in that story. So now let's look at our velocity graph. Okay, this point right here is an incorrect answer. This is the point in which his velocity, see how his velocity is increasing, then all of a sudden it drops, his velocity is dropping. So that's the point where he realizes he forgets his acorn, and then he just slows down slowly. So he's basically going full speed, and then now his velocity is slowing down. Still going forward, but slowing down. This is the point where his velocity is 0. Do you guys agree? So this is a velocity graph. Do you see how this is where the velocity is 0? So that's the moment when he stops. He stops when his velocity is 0, and that's when he turns around. So anything past this point, see how I'm in a negative velocity now? That means he's running backwards. So my answer is not this one, not this one. He stops when his velocity is 0, which is right here. And that is t equals 4. And it says, give a reason for your answer. You could write down what I told you. Okay, moving on. It says, what time does the squirrel arrive back at building A? So just if you understand that he was going, understand he was going in one direction, and then he, give me 1 second. Let me reopen it. So if you understand what I just told you about someone speeding up and slowing down, and realizing that it was, realizing that he went the wrong way, then you should understand in the opposite direction. So now he's going backwards, and then this is how fast he's going in the opposite direction. And then do you see this little down spot here? So now what he realizes that, or this is where he picks it up, because now his velocity is increasing again and going in the right direction. So he's going, and here, when his velocity is 0, So see how his velocity is still going negative, or if you think about it left to right, at this portion up here, he's going to the right. Okay, so when the squirrel is running, he's going to the right. Okay, so he's running. Still going to the right, but now he slows down, and this is when his velocity was 0. Okay, or this is when he realized, or not really realized, but exactly stopped and turned around. And this section below, when the velocity is negative, that means that's when he's running left. So he's running left. And now, I guess he's approaching the acorn. So now he's still running left. Remember, he's still below. He's still running left, but less left. So here's when he's slowing down in the left direction. I know it's hard to understand, but think about it like you're running backwards. So pretend you're running backwards, and then you slow down, but still running backwards. That's what this means right here. That's what the second means. And then velocity is stopped. Okay, his velocity is stopped. So what that means is that this is where he reaches or goes back to. This is when he goes back to get his acorn, because now his velocity is stopped. So the answer for B, when does he arrive there, is 7. It says find the total distance, and this is probably the last one I have time for. I'll go for the rest of it tomorrow. It says find the total distance the squirrel travels during 0 to 20. So if this is a velocity graph, and I want to know how much total he went from 0 to 20, what I need to do is take the the antiderivative between 0 and 20. So here's 0, here's 20. If I find the area under the curve, it tells me how far he went. Okay, and that's what antiderivative means, or that's why we did all those rectangles, or we cared so much about trapezoids, is because if I find the area under the curve of a velocity graph, I could find total units. Okay, so I'm not going to have time to do this, but what you're going to do is take the area of this triangle, take the area of this triangle. I would essentially draw or write out like mini pieces. So here's a triangle, oops, here's a rectangle, trapezoid, and then trapezoid. So sorry it's messy, but what I meant was Well, I'll talk to you later. Have a good day.